For this video, I'll be working through question 4 of the 2018 Scholarship Physics exam. Right, question 4. Spring of length L and spring constant K is cut into two pieces, L1 and L2, with a spring constant of K1 and K2 respectively. Show that essentially 1 over the total spring constant is equal to 1 over K1 and 1 over K2 plus 1 over K2. To solve this question, you need to know sort of one thing. That is that the tension, I'll just write it down, tension across the spring is uniform. Across the spring is, I say uniform, I'm going to put the same everywhere. Everywhere. I'm not going to fit that. Right, there we go. It's the same everywhere. In other words, so capital F, that's the total force, is equal to the total spring constant times the total extension, which is also equal to the spring constant of K1 times L1, how much this one's been extended or compressed. I don't know if it's been extended or compressed, it's hard to tell. And that is equal to K2L2. Because everywhere along the spring, it's exactly the same tension or compression or whatever, because it is the same spring. Right, and we've got another thing, and the length is equal to L1 plus L2. There we go. Right, so in other words, so the total force is equal to K, and then I'm going to put in, substitute the total length for L1 plus L2, L1 plus L2, and this is where a little bit of algebra wizardry comes in. You just sort of need to know that you're going to have to substitute. L1 is equal to the total force over K1, so that is going to be equal to K, and then we're going to go, so the total force, because it's the same force everywhere on the spring, we've just established that, so over K1 plus, same again, over K2, right, and that is equal to, again, the same thing as what I started with, just reiterate that, and from there, I am going to explain this out a little bit, and then we'll cancel some stuff off, and then it turns out we'll get what we're looking for. So we have K F over K1 plus K F, messy, over K2, and that is equal to, again, the total force. As you can see, yeah, we can cancel out the forces because it's all the same force. So cancel, 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 and then when you do that, divide by F, you get, this is just equal to 1. And if you divide by K, you get, so this is divided by F and divided by K. You should get 1 over K1 plus 1 over K2. That is equal to 1, because F divided by F is 1. You divide by K total. Sweet. Right, so the main takeaway from this one is that, yeah, the force throughout everything is constant. If you didn't know that, you would have been completely stumped. Right, consider the situation above where two springs of spring constants K1 and K2 are connected together with masses, which sit on a frictionless surface called equilibrium links, L1 and L2 respectively, and the center mass of M1 lies at X1 right in the middle, and the center mass of M2 lies at X2. M1 is held, so we hold M1 while a force F0 or F0 is applied to mass 2 in the direction of M1. So we're going to check a force like that, and let's call that F0. Sweet. Using the result of part A, show that the change in position for M2 is equal to change in change in displacement of X, is equal to F0 times all this stuff. So basically, I know the answer. This is just the displacement's the total force divided by the total spring constant. How this is related to the total spring constant, we'll get to. So we'll do that now. So we know from 1 over k is equal to 1 over k1 plus k2. Oosh, that's messy. Using, I suppose, like year 10 fractions, we're going to make this one whole fraction. And to do that, you times the two denominators together. So we get k2 over k1, k2. Oops, there should be k2 down there. I hope you can see that. Plus k1 over k1, k2. So it's just when you add random fractions, let's add like 3 over 2 plus 4 over 3. You times the denominators together, and then you go 3 times 3, that's 9. So you get 3 over 6 plus 8 over 6. Yeah, it's the same process, exactly the same process. And that is going to be equal to k2 plus k1 over k1, k2, and that is equal to 1 over the total spring constant. Now we know that change in x2 is equal to f0 divided by k. We know 1 over k is that, so that is pretty straightforward, just to say f0 and k1 plus k2 divided by k1, k2. Boom, easy. Next question. Describe, so we've got a whole lot of rubbish. Both masses are now released simultaneously. The values of the masses and spring constants are all of that. The force is that. Assume the mass of the springs is negligible compared to M1, M2. So basically the springs are weightless. That solves a whole lot of problems for us. Describe in detail the resulting motions of M1 and M2. So I'm going to flick this over, and we'll just do this visually. So put your finger there, you've sprung it in, push it a little bit, and then you go 3, 2, 1, boom, and then you move your hands away. When you do that, you're not really applying an external force to the whole system. You're just compressing the system a bit and then letting it go and letting it do something. So the center of mass is just going to stay where it is because you haven't really shunted it. You've held that in place. You really just compressed the spring or pulled the spring apart. Either way, it doesn't matter. In this case, we've compressed the spring a bit, we've weighted, and then we've moved our hands, and it's going to oscillate back and forth. The heavier one will probably oscillate with a lower period compared to the lighter one, depending on the spring constants. If the spring constants are more or less, and just remember, I'm going to write T equals 2 pi square root K over M. That's the general oscillating formula for a spring bouncing in and out, upside down, or it could bounce however it wants. This is the relation to the period. The amplitude is just going to be what it is. It's just going to be constant. They'll be oscillating opposite phase to each other. So when what do we want? We squeezed it in. So essentially, we could squeeze this in. When we release it, they're going to go out and then in and then out and then in and then out and then in and then out and then in and so on and so forth. As long as there's no bleed off of energy. So I'm going to pause the video, write the answer all nice and neat, and then move. Alright, so I've said as both masses are released simultaneously and there is no external forces / friction. It's an internal. You can think of the system as like an internal force. The center of mass won't move. The boxes will oscillate with opposite phase, which just means when they're going like that, opposite phase. In simple harmonic motion. Simple harmonic motion, the definition for that is linear force, linear displacement. This is what's happening here. It's boxes. I'm assuming the springs are obeying Hooke's law. It seems to be. And they aren't identical in the amplitudes as they aren't identical. So one box could be heavier than the other, so the amplitudes will be different. Right. And the spring constants could be different as well. The spring constants are different. So I had no idea what the amplitudes are. You could figure it out, but we're not asked to, so just not worry about it. Show the maximum velocity reached by mass. M2 is 0.4 meters per second. Right. So the technique to answering this question is a universal technique across all of these scholarship exams. This is what they love to do. You use momentum conservation and substitute it into an energy formula to solve something. So 2017 question 2, you had like something falling, landing on the spring, compression. You're getting kinetic energy transformation, or gravitational potential into spring potential, and you've got a momentum conservation going on in that collision time, during that collision. Right, so net momentum, when I write in the word, this is a pretty heavy question as well in terms of algebra, is 0. So the total momentum is 0 because the center of mass isn't moving, which is kind of nice. Otherwise, I'm not sure if you'd be able to solve this. You probably would. Be a bit of a hassle. So P total is equal to m1v1 minus m2v2, because both boxes will have momentum of some sort, and that is equal to 0. In other words, they're equal to each other. So that is kind of nice. Right, total energy is half m1v1 squared plus half m2v2 squared. And what the heck is this? So this is the total kinetic energy, and that is going to be equal to the total spring potential, because initially you compress it, it's got 0 kinetic energy whatsoever. You let go, boom, all that potential energy will then slowly transform into completely kinetic energy at the maximum velocity, and then it'll go out to its maximum point, all back into potential energy, and it just oscillates between those two forms of energy. So that is going to be equal to half, total spring constant times the little displacement that you gave it, because this is the energy that you added to the system. So it's half, delta x2 squared. Now, what do we need to do? Right, we need to find the total spring constant, which we can easily do. That is just going to be equal to 1 over bracket 1 over 5 plus 1 over 10, because they are the two springs, 10 and 5, and that is going to give me, if you put that in your calculator, 3.3 Newton meters, because that's just a unit for springs. What else do we need? We need the total displacement. Delta x from over the page, just equal to the total force exerted divided by the spring constant. That's going to be 2 over 3.3, and that is equal to 0.606 meters. That is the total compression. Right. I will write out the energy equations we're going to have, but I'm going to get rid of the halves, because there's halves all through it, so I'm just going to get rid of them. They're not that useful. So we've got m1v1 squared plus m2v2 squared, you can see that, and that is going to be equal to k delta x2 squared. This is a number, this is a number, all the masses are numbers, that's an unknown, that's what we're trying to find, because that's of mass 2, so we're trying to find the velocity of mass 2. We have no idea what the velocity of mass 1, and this is the neat thing with this conservation momentum formula. What we can do is we can show that V1 is equal to m2v2 divided by m1, because we can move that, we can move this to that side of the equation, and we can move the m1 underneath, and we have this. So now we're almost there. What we need to do is substitute this in, because I know what the mass is for both of them. I know what this whole number is. I'm not sure what it is exactly, but I know that's 3.3 and that's 0.6 squared. Right, so we're going to substitute this in. I might just leave it in its algebraic form and then get your way to the end. Right, so we're going to have m1 bracket m2v2 over m1 squared plus m2v2 squared. I'm going to leave this as just k delta x2 squared. And now I am going to, what am I going to do? I'm going to pull out v2, and you can cancel some stuff out. So this ends up becomes m1 squared, and that m1 cancels that out. So you get v2 squared bracket m2, because that's that one there, plus what would have been this here expanded out. So that would have been, well, you got an m2 squared for sure, and then you're going to have an m1 over m2 squared, so it's going to be divided by m1 bracket, and that is going to be equal to k x squared. Right, and now you can see v2 is going to be equal to the square root, if I can fit all this, of k delta x squared divided by m2 plus m2 squared over m1. And if you put this in your calculator, you get 0.397, at least that's what I got, and that is equal to 0.4 meters per second negative 1. Right, here we go. So this is a really, really common trick. In nuclear physics, you can do it with like total momentum of an electron coming in, hitting something, bouncing off, and a photon's released with some sort of momentum, and then you've got the conservation of momentum of the collision, and then you substitute that into an energy formula to find out a velocity of such particle, or the wavelength if you're dealing with energy, because energy relates to frequency, which then can just be related to wavelength anyway. This is a bit of an out of nowhere question. Oh no. Explain how the motion of the system will be altered if the mass of the springs were not negligible compared to M1 and M2. Right, so if you increase the mass, it's not going to change anything to do with the energy of the system. The energy of the system is entirely due to how much you press it in and the spring constants. You haven't changed either of them, so the energy of the system will still be the same. You will increase the mass essentially you increase the whole mass of the whole thing. So we're our formula over here. The period is going to, if this increases, the period should decrease. The amplitude won't change at all because, as we can see up, hold on. Amplitude won't change. No, it won't, because you put the same amount of energy into the system. At some point, the system's not moving. That's when it's at its maximum displacement. So the spring constant hasn't changed, so you should have exactly the same amplitude. Right, so I'm going to pause it, write everything else, and then discuss. Alright, so I said the centre of mass won't change, amplitude of the oscillations won't change, as the kinetic energy is still zero at the endpoints. Period will increase as essentially the period is equal to 2 pi square root of the spring constant O divided by the mass. You haven't changed the spring constant, but you've increased the mass. Total energy will be the same as the energy that's given to the whole entire system is just half kx squared, and none of that has changed.